In presentation 11, I talked a little bit more on how you can identify what you may have in your ore or concentrates, and how you may be able to estimate the percentage of concentration. In presentation 12, I introduced the charge table. Well, in this presentation, I will be showing and discussing the actual use of this table. I am Rob Boyko, Boyko Mineral Exploration, and welcome back. The example I'm going to use is a typical gold quartz type of ore. The precious metal concentrations within this ore are to be determined and is not subjected to any flux calculations. It is assumed that the person that will be conducting this experiment has estimated the ore contents of consisting of 50% chalcopyrite, 8% nickel arsenide, and 42% quartz. After your sample has been crushed and or pulverized to minus 100 mesh, then homogenized, that is, being thoroughly mixed, it must be weighed out. The textbooks always refer to assay ton weight. A calculation must be done to be able to measure out the correct amount in grams. This is simply done by multiplying the magic number of 29.166 by the desired assay ton requirement, being 0.25 assay tons in this case example. The ore consists of a lot of contaminants. Therefore, the required amount of 0.5 of an assay ton is not used. If you are not familiar with the charge table, I recommend reviewing the previous presentation, which is part 12, the fine art of fire. The constituent material in this ore sample contains sulfur, and therefore will be treated as a class 2 ore. Step 2 is a decision made based on the ore class type. In this case example, the ore contains sulfur with impurities. The sulfur complex makes it a class 2 ore with contaminants. Therefore, a subsilicate degree is used. This means that a ratio of 1 to 2 is used in the calculations to determine the amount of silica that will be required for the charge. The silica is the acid portion, and the base metals and flux constituents are the base elements of the charge. The representation here is that 1 part silica is fused with 2 parts of base material. This series of calculations will be shown, as it is step 5 in the charge table. In step 3, it is a calculation of the amount of soda ash to be mixed with the sample. This is the easiest of all calculations. It's an equal amount to that of the sample weight. Since there are 7.3 grams of sample that will be analyzed, the amount of sodium carbonate to be mixed with the sample will be 7.3 grams. Before moving on to step 4 of the charge table, all our calculations are based on molecular and molar weights, as well as the physical weights consisting of the ore or sample. This requires a conversion to grams. This case example shows that the chalcopyrite was 50% in concentration, nickel arsenide at 8% and quartz at 42%. This equated to 3.65 grams of chalcopyrite, 0.584 grams of nickel arsenide, and 3.066 grams of quartz. We also need to know what the individual molecular weight is in grams. In order to do this, the periodic table is used to calculate the molecular weights of the chalcopyrite, nickel arsenide, and the quartz. Simply adding up the individual elemental molar weights listed in the periodic table gives us the molecular weight of each constituent. In addition to the individual elemental weight of each element in grams, this also must be known. This is simply calculated by dividing the elemental molar weight by the molecular weight of the compound, then multiplying the number of grams in the ore. The calculations are shown. For the chalcopyrite, which contains copper, iron, and sulfur, the molecular weight is 183.5 grams. The molar weight of the copper given in the periodic table is 63.5 grams. Dividing the 63.5 by the molecular weight of 183.5, then multiplying by the physical weight of the chalcopyrite in the ore, gives us a result of 1.26 grams of copper in the sample that weighs 7.3 grams. M, that is capital M, stands for the molecular weight, and ATWT stands for atomic weight, which is molar weight. Now that we have this data, we can move on to step 4 in the charge table. In step 4 of the charge table, the amount of litharge required for the charge is calculated. In this case example, the ore is a class 2 ore. It also contains some impurities, being copper and the nickel. As calculated from the previous slide, there is 1.26 grams of copper in the ore sample and 0.26 grams of nickel. It also contains arsenic, which will be dealt with when we get to step 9. The end result is to obtain a 28-gram button containing the precious metals. As shown in an earlier presentation, 30 grams of lead oxide is required to produce a 28-gram lead button. The rest of the lead oxide is used to fuse all the gangue material in the slag. The more gangue material, the more lead oxide will be required to oxidize the base metals. By following the charge table as shown here, 182 grams of lead oxide will be required for the charge. In a previous presentation, I discussed briefly the process of the base metals and fluxes oxidizing and or reducing during fusion. That is to say that, for example, the copper component in the chalcopyrite will oxidize to copper oxide. The only exception is the litharge, which is already lead oxide. During fusion with silica, it will remain as lead oxide. I also discussed the silicate degree, which is a ratio between the oxygen atom of the acid, in this case the silica, and the base metals or basic flux material. In this case example, I have shown that the silicate degree used for the calculations is subsilicate. Each component in the ore must be calculated separately. In this case, as shown in this and the next slide, is the copper, iron, nickel, arsenic, litharge, and the soda ash. Each item starts with the balanced equation as shown. Notice that the silicate degree is subsilicate, and for each oxygen atom of the basic material is doubled, which is a ratio of 1 to 2. Each oxygen atom in the base component is doubled to that of the silica's oxygen atom. That means that for every 1 molecule of silica, which contains 2 oxygen atoms, there will be 4 molecules of copper oxide, which contains 1 oxygen atom. This equates to 4 oxygen atoms in the base material and 2 oxygen atoms in the acidic material, which is a 1 to 2 ratio. Since there are 2 copper atoms in the copper oxide, and there are 4 molecules of the copper oxide, it shows that there is a total of 8 copper atoms in the 4 molecules. Because there are 8 copper atoms, that means there must be 8 copper atoms in the chalcopyrite. Since there is only 1 atom in the chalcopyrite, there must be 8 molecules of chalcopyrite in the ore material to make up the total of 8 copper atoms. Knowing what the base equation looks like, the needed amount of silica for each item can now be calculated. Calculating the molecular and molar weights using the periodic table was discussed during the earlier discussion on concentrations within this presentation. The actual calculations are simple as shown. As mentioned and shown in this slide, the litharge, which is lead oxide, is already an oxide in its lowest oxygen state. It does not change. Once all the calculations are completed, the results are simply added together. The total is the required amount to be added to the charge, less 1/3. In this case example, The full amount of silica, which is 14.79 grams minus 3.066, will be the amount to be mixed with the ore sample as a flux component. The 3.066 grams is the amount that was in the ore sample. 11.72 grams is the required amount to be added to the charge. In the previous presentation, I introduced the charge table. Step 9 of that table refers to special cases. In this case, the addition of borax will be omitted. This is due to the copper and nickel component in the ore in this case example. The addition of borax would be step 6 in the charge table. Step 6 was omitted due to the amount of contaminant in the ore sample. However, the size of the required lead button, which is 28 grams, still needs to be dealt with. Being a Class II ore material, the reducing power of the litharge to elemental lead must be determined. The reducing power is simply calculated as the number of moles of lead times the lead's atomic weight divided by the moles of ore and the molecular weight of the ore. The amount of lead that will be produced is simply done by multiplying the weight of the individual constituents in the ore material by the reducing power that is calculated. It is important to start with a balanced equation as shown. When the flux material is added to the chalcopyrite, 15 molecules of lead oxide will be reduced to lead, which will result in 15 atoms of elemental lead. The same is with the nickel arsenide component in the ore. As shown, the chalcopyrite result is the lead oxide reducing to 30.9 grams of elemental lead. For the nickel arsenide, we should get 6.69 grams of lead. Totaling the results will add up to 37.59 grams. That's a little more than the required amount of 28 grams. 9.59 grams of lead must be inhibited from being formed. Therefore, niter is used. The potassium nitrate has an inhibiting factor of 4, and therefore by dividing the amount of excess lead by the factor of 4 will give us the amount of niter required to inhibit the 9.59 grams that would be in excess. The constant 4 is the oxidizing power of niter. If the lead button produced was less than the required size and weight, flour would be added to further the reducing of the lead oxide. In this case, the amount of flour required would be equal to the amount needed divided by the constant 11, which is the reducing power of the flour. Niter is an oxidizing agent. It can be thought of as an acidic substance such as nitric acid. To counter the acidity aspect of potassium nitrate, additional soda ash is added to the flux mixture. For every 4 parts or grams of niter that is added to the flux, 1 part or 1 gram of soda ash is required. As we added 2.4 grams of niter to inhibit the excess lead, we would have to add 0.60 grams of additional soda ash to the flux mixture. Same with the excess silica, that is, if there was some, additional soda ash would have to be added to fuse the excess silicon dioxide. For the excess silica, the use of a balanced equation would need to be used as shown. In presentation 12, I introduced the charge table. Now, step 9 in the table is additional instructions pertaining to special cases. Contaminants such as copper, nickel, and so on is covered in step 9. Note that there is also arsenic in the sample. There is 0.33 grams of arsenic in the ore, therefore 0.33 grams of soda ash is added to the top of the cover layer. Since the ore in the case example contains both nickel and copper as well, a cover layer consisting of 4 parts soda ash, 2 parts borax, and 1 part silica is required. This mixture is not added and mixed into the charge. It is simply placed on top of the charge. The calculations shown are for reference regarding the calculations required to calculate the amount of ingredients for the cover layer. In this case example, the Class 2 ore was composed of 50% chalcopyrite, 8% nickel arsenide, and 42% quartz. I have shown the calculations in respect to the charge table. Adding up the calculated results summarizes the required flux material, the quantity to be used, and the requirement of any cover layer that would be needed. The flux requirements for this ore are shown. Your ore samples or concentrates will vary in constituent due to the nugget effect and the homogeneity of the ore. However, if the ore sample or concentrates are from the same source material, the same summary table may be used satisfactorily for all the samples as a basic charge. Keep in mind that the sample material does and will change in properties if the sample is from a different source. There may be times that a little experimentation may be required and the charge table tweaked. By using the charge table and calculating your charges, your results will be more accurate than just using some recipe from YouTube. The summary table shows what would be required to fuse an ideal slag and create the required button containing all the precious and noble metals that would have been trapped in the matrix of the ore used in this case example. In presentation 12, I discussed the charge table and what it is used for. In this presentation, I showed and discussed the process of calculating the charge requirements for a Class 2 ore in regards to the charge table. In the next presentation, I will be showing the calculations in regards to the charge table for a Class 3 ore. Those calculations will be the same for Class 1 ore. I hope that this presentation was useful to you and will benefit you in creating your own flux recipes. If you found this presentation interesting or useful, or if you know someone who will benefit from this information, please give it a like, a thumbs up, and a share. This is my only reward. I am Rob Boyko, Boyko Mineral Exploration, and I thank you for watching.